Hello everyone. So this is the continuation or the part 3 of our series of discussions about mathematical physics concerning vector calculus, where we are solving certain problems in vector calculus. Today we're going to show that the divergence of the Coulomb or gravitational force is 0. As we know, the Coulomb force is responsible with the interaction of two charges or two charged particles, while the gravitational force is responsible with the interaction of two objects with masses m1 and m2. Now, both the Coulomb and gravitational forces are actually inversely proportional to the square of the separation distance between the two particles. So we solve this one by applying the product rule. We have the first, the second, plus second, the first, or the first variable multiplied by the derivative of the second variable plus the second variable multiplied by the derivative of the first variable. So here we have our first variable is r to the negative 3. Okay, anyway, this is commutative. So we have r to the negative 3 times the divergence of r plus r dotted to the gradient of r to the negative 3. And obviously, as we know, r to the negative 3 is given by this, if we're going to expand it. So we have x squared plus y squared plus z squared to the negative 3 halves. And as we know, the del, or the gradient operator, is also given by this. Now we have partial with respect to xi hat, plus partial with respect to yj hat, plus partial with respect to zk hat. And this is dotted to the position vector. So we have the divergence of r. And as we know, the position vector is xi hat plus yj hat plus zk hat. And the thing that we have to consider here is that we have to perform first the divergence before we multiply it with r to the negative 3. Now here, as we know, the unit vectors, or any unit vector that is multiplied to itself, is of course, that is equal to 1. And if the angle between two unit vectors is 90 degrees, then the multiplication or the dot product of this unit vector dotted to another unit vector is, of course, equal to 0. So here we can see that only those that have the same unit vectors will survive. So we have partial with respect to x times x, or partial with respect to x of x, that is equal to 1. We have partial with respect to y of y, that is equal to 1. And we have partial of z with respect to z, partial with respect to z of z, that is equal to 1, which means that we have 1 plus 1 plus 1. So this one inside this yellow box is actually equal to 3. And then we multiply it with x squared plus y squared plus z squared to the negative 3 halves, or just simply equal to r to the negative 3. Now, in the second part of this equation, this second term, we have r dotted to the gradient of r to the negative 3. Okay, so we have to write first the position vector, which is xi hat plus yj hat plus zk hat. And this is dotted to the gradient of r to the negative 3. As we know, r to the negative 3 is x squared plus y squared plus z squared to the negative 3 halves. And the gradient vector is still the same. We have partial with respect to xi hat plus partial with respect to yj hat plus partial with respect to zk hat. And this should be distributed with this r to the negative 3. So we have partial with respect to x of r to the negative 3 I hat plus partial with respect to y of r to the negative 3 j hat plus partial with respect to z of r to the negative 3 k hat. And then after performing this one, or after getting the partial derivatives, we then dot it with our position vector, and we can find out that this is actually equal to 3r to the negative 3. So basically, if we're going to get the divergence of the Coulomb force or the gravitational force, basically the gradient is equal to 0. So I guess that's all. If you have some comments or questions regarding our discussion, you may type your comments in the comment section, or you may just send me an email. Please don't forget to subscribe, and if you're not able to watch our previous videos, you can always watch them on our YouTube channel. Thank you.